You are listening to Science Coast with Mallory Havens and
Chris White.
And our guest,
Ryan Hooper.
Welcome back, Ryan.
Thanks for having me.
So Ryan is one of the particle physicists that we have on faculty here at Lewis University. And Ryan has been involved with the Muon program at Fermilab. And the Muon program at Fermilab involves many experiments. But it is the primary initiative right now at the Fermi National Accelerator Laboratory in Batavia, Illinois. So we thought we'd have a conversation with Ryan about the Muon program that he's currently working on. So can you tell us a little bit about that experiment?
Of course. So I'm a collaborator in what's called the Mu2e experiment. It is currently under construction at Fermilab, as Chris said. And the primary goal of this experiment is to observe, hopefully, a process that has never been observed in nature. And quickly, the process is the transmutation of a muon, which is a somewhat massive cousin to the electron, a muon, in some sense, directly transmuting into an electron without any associated neutrinos buzzing around. So this is a transmutation from a muon directly into an electron, and that process is so rare that it's actually never been directly observed. The one interpretation of that is if we do see this process, this will be an indication of some unknown physics going on behind the scenes that we've never seen before. So it's designed to be a discovery level kind of experiment.
So is this something that you know happens, or you're trying to see if it ever does happen?
So within the framework of what we call the standard model of particle physics, you can draw a complicated enough Feynman diagram to predict that this could happen at something like, 10 to the negative 60th level.
Okay.
Just to give it's statistically so small that it's effectively zero. And the point of the Mu2e experiment is to run with enough statistics that if you do see this, only some sort of new physics that's not in the standard model actually must be going on to account for this increased rate that we see of this process. So it's really looking for a process that technically could exist, but it exists at a statistically zero level. But this experiment will run, and if we do see it, then statistically this will be a very statistically significant event if it does occur.
So you're basically asking the question, like, do we understand the physics of this enough that our prediction of zero is correct, or is there this whole other area that we need to explore?
Yeah, in the particle physics language, I think it's referred to as a neutral current, where you're taking a lepton, like a muon is a lepton, and changing it into another charged lepton. So a muon has a charge of -1. An electron has a charge of -1. So if I can get a muon to turn into an electron directly, then that has implications. There's only so many ways that particles can interact with other particles. And to Ryan's point, it has to be a very convoluted, multi-order process to have a charged lepton turn into another charged lepton, without there being neutrinos.
The key is without neutrinos being running around. And we call this process a lepton violating process, a lepton number charged lepton violating process, because the muon, we think, at least the standard model, it holds lepton type sort of sacred. So if I start out with a muon lepton creature, right? My process at the end, in the standard model, I need to end up with that same number of muon lepton-like creatures.
Yeah, there still has to be something that has muon name associated with it.
Yes.
There's like a flavor associated with a muon that can't disappear.
Right.
So you can't turn a leprechaun into Dracula.
Exactly.
Right. Without some other leprechaun-like things bouncing around, which in this case is usually neutrinos.
Yeah, and this is a bigger issue where there's multiple experiments, like double beta decay is similar.
Yes, right.
Neutrinoless double beta decay, excuse me.
Yes.
Double beta decay happens, but neutrinoless double beta decay is a different story.
Right.
So would the neutrinos normally account for the mass difference between the muon and the electron? Or, because you said the muon is like a big cousin, right? So I'm assuming big means more mass.
Yeah, but mass and energy are the same thing, so it's really the velocities of things. So the kinetic energy takes into account the mass difference.
Okay.
Yeah.
I can accept that.
Yeah. Yeah.
So if you had a muon that was effectively at rest in its own, inertial reference frame, it could decay into an electron, but the electron would have a large amount of momentum and kinetic energy. And then the problem is how do you conserve both energy and momentum at the same time while doing this transition? And so there's a lot of physical parameters that are involved.
So how do you test this?
Well, we are going to build, in the process of building, a pulsed proton beam. So there's a few chain of events, but it basically boils down to a proton beam that's pulsed. When I say pulse, I mean well bunched in time. All right, and there's some reasons for that. But we take a proton beam, we're going to run it into essentially some tungsten, and many of the byproducts of that violent amount of stuff coming out are actually things called pions. Okay. And we do that.
Sounds delicious.
Yes, we all, this time of year especially, we all like ourselves some pecan pions. Yes, sir. And we do that in a region where we have a level of really good control over a magnetic field, and we can steer some of the pions that sort of that backscatter out of this, and we start building initially, shall we say, a pion beam. And we do know that pions will then very quickly transmute to muons, and then we basically snake them around in literally an S-curve looking set of magnets. And then at the end of that S-curve set of magnets, you essentially now have a muon beam. Okay? So you create a muon beam, and then you run that muon beam we're going to start with an aluminum target. So we basically take those muons, run them into the atomic shells around the atoms of the aluminum, and then what you look for is a signature of that muon essentially being captured in an orbit briefly around the aluminum nucleus, and then you look for that muon transmuting into an electron with no associated neutrinos. Now then you're going to ask, well, if you know anything about neutrinos, they're hard to see. Mm-hmm. Well, if you do the energy balance on how this all works out, there's a pretty well-defined and unique energy signature that would come out of the electrons from that muon decay. And essentially then you build a tracking system and a calorimeter, and you build some detectors a little bit downstream of that are really good at seeing that type of energy signature from that electron. So that's how you do it. I mean, that's what's being done right now. We're putting this into place to start taking some data over the next couple of years.
So it seems to me like a lot of particle physics is building new technology to try to observe things.
There's no particle physics store that you can go to buy the apparatus. And that's one of the things in our field. We train way more students than can actually be employed by the particle physics research community. And the training that students will get building and operating particle physics experiments is absolutely translatable into the corporate world. So a large number of the graduate students, and there's needs for developing artificial intelligence. In some sense, artificial intelligence algorithms were being used by particle physicists decades ago to try to do better data analyses. Yep. And so the grad students who are trained in these, in these modeling techniques were snapped up by industries. I remember when I was finishing my PhD in particle physics, I was asked to interview with Shell Oil Company. And I remember asking the interviewer, because I was a young guy who didn't really understand the world. It's like, hey, I'm getting a PhD in particle physics. Why are you interested in me? Mm-hmm. And they said the problem-solving skills that you've developed as a particle physicist will be more useful to us in the long run, and that's what we want.
Yep.
So we want you to help us go seek out oil fields. And I was like, but I don't know anything about geology. And said, oh, we'll teach you the geology.
Right. That's right.
What we actually want is your problem-solving skills.
That's right.
I think that's kind of interesting. As a molecular biologist, I've never invented a technology or built a brand new piece of equipment. I take existing methods and apply them in new scenarios to discover things. Whereas you guys kind of take the opposite approach. You build technologies to try to find things. I take technologies to try to find things.
Yeah,
Sort
that's
of.
fine.
I mean,
yeah, and a
different
lot of
approaches.
So a lot of the training that fundamental physicists get, experimentalists get, is how to build things.
Right.
And I remember as an undergraduate, one of the very first things when I took my first job working in a research lab as an undergraduate, the first thing they did was take me down to the machine shop. And we're going to teach you how to take this block of aluminum and turn it into something else, because every apparatus that is used is custom built in some sense.
Right.
And now the 3D printing has completely revolutionized the field. So instead of trying to, and I know that when I was a student, I would spend a lot of time down in the machine shop talking to the machinists about, can we make something that looks like this? Can we make something that looks like that? And they'd be like, what are you trying to do? And so we'd talk to them about what we're trying to do. And they'd say, okay, let's come up with a design for what this equipment should look like. Nowadays, people 3D print things all the time. So if you want to do a lot of prototypes, there's a lot of build a prototype. Okay, that didn't quite work. Okay, build another prototype. Okay, that didn't quite work. Okay, build another prototype. Oh, this one works. Great. Let's mass produce it. And then you put together your experiment.
Yeah, I think it's fascinating just the different approaches we can take to solve similarly complex problems.
And at the end of the day, it's always like, okay, what is it that we want? Well, we want to take protons and accelerate them to this high energy. All right, so what do we need to do? Well, we need to invent new superconducting technologies so that we can create magnets that have fields large enough to be able to do this. Okay, great. Now that you've done this, oh, by the way, these superconducting magnets can be used to do medical imaging too.
Right.
So this is kind of a crazy off-the-wall question for both of you guys, but when you think about particles from particle physics, how do you visualize them? Because when I think of like
billiard balls.
What? Billiard balls? Because when I like, whenever I think particle physics, I have like the blackness of space and then individual particles or balls, but not billiard balls in my mind, and kind of
And
imagine
they all have the
like
number 8 on them.
halos of energy. I don't know. What do you guys visually think of?
So my initial visualization is not too far off from Chris's billiard balls, right?
Really?
Yeah. That especially when you're talking particle physics and like protons and things running into each other.
Are they on the green felt?
Yeah, no. But we know that that's actually not a really good representation of what's going on. So, I mean, if you learn enough quantum mechanics like we've had to, you go, well, that picture does not suit things real well. But my default setting is a very, shall we say, macroscopic, planetary sort of, classical physics view. And I think there's nothing wrong with that. I think to me, that's a good place to start. But to be fair, shall we say quickly, but it still takes effort for me to visualize them as like overlapping wave and wave, quantum mechanical, probability densities and things of that sort. I mean, I can see it that way in my mind's eye, but my default setting, my initial model looks very classical. But then when I need to, shall we say, I can switch over and sort of visualize things in a much more wave picture pattern. But that still takes effort for me to do. I mean, it's something I still have to kind of switch on.
Oh, okay.
So the size of the ball is, in some sense, directly related to the probability that it might interact with something. So we tend to think of like neutrinos that have very low quantum mechanical probability of interacting as being really, 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 really small, tiny balls. And something like a proton that has a very large probability of interacting with something can be a large billiard ball or a beach ball. And that actually gets translated into something called a cross-section, where instead of talking about a probability, you can then define a physical area measured in square meters, which is directly translatable to the quantum mechanical probability of an interaction. And it makes it easier to think about, well, if I take this type of a particle and I put it through this type of a target, what's the probability that it'll interact? Well, if I then define what the cross-section for this interaction is, measured in square meters.
Bigger is more.
Bigger is more. And further, I can do a calculation where I simply try to decide, from a classical perspective, if I have a bunch of targets that are all this size, 1 square centimeter, and I have a bunch of objects that I'm shooting at it. And by the way, these 1 square centimeter objects are all separated by, 3 meters or whatever. So you define what the lattice looks like. And then I'm shooting it with these little bullets, and the bullets have this size. Then I can do a classical probability calculation where I just say, well, I have like a 3% probability that they're going to hit each other. And it actually works out.
And it works out quite well, actually.
I like that visualization. I think you could use it too, like I use to explain like electrophoresis and molecules moving through networks as a moose versus a mouse running through a forest. So a mouse can slip between things more easily and not get tangled up, whereas a moose with its giant antlers is going to get stuck and slowed. So it's kind of a similar thing, like just imagining sizes. I like that. Now I'm a particle physicist, I'm pretty sure.
Yes, you are. I'm pretty sure.
That's right.
Figured it all. All I needed was a beach ball versus pebble analogy. I got there. All right. Well, the views, thoughts, and opinions expressed are the speaker's own and do not represent the views, thoughts, and opinions of Lewis University. The material and information presented here is for general information purposes only. The Lewis University name and all forms and abbreviations are the property of its owner, and its use does not imply endorsement of or opposition to any specific organization, product, or service. This podcast was produced in the WLRA podcast studios at Lewis University. Visit lewisu.edu for more information about Lewis University. You've been listening to Science Coast with Mallory Havens and
Chris White
and
Ryan Hooper.
Thanks.
Bye.